Hello! In this video, we are going to use octave to help us understand a bit more about a simple statics problem. So let's say we have this bar here, this rigid bar. It's being held up by a cable here in gray. And if we held up this bar at an angle alpha with a horizontal, and this cable having an angle beta relative to the bar, we want to calculate what is the tension being applied to this cable. So the first thing we need to do to solve this problem is to draw a free body diagram for this bar. And initially we could think of having the reference frame like drawn here with the x-axis and the horizontal and y-axis perpendicular to it. And we would have our weight here of the bar applied at center and the components in x and y of the tension applied at this point. If we would go on and apply the sum of moments around this point O here, we would be able to find the expression for the tension. However, maybe a simpler way is to have our reference frame like so, with the y-axis along the direction of the bar and the x-axis transversal to it. So the components of our weight in x and y directions would be here, and the components of the tension in x and y directions would be like so. If we would go on and find the expressions for these components dx and wx, we would see they would be simply given by t times sine of the angle beta, which is replied here. This angle is repeated here, and the component in x of the weight would be given with the help of the angle alpha, this angle here, which is repeated here, and we see that the component in x is w cosine of alpha. So we apply the sum of moments around this point here, and we can find this expression for the tension given in function of the weight, the angle alpha and the angle beta. So let's go ahead and try to use octave to calculate this tension here. So we would need these initial angle alpha. Let's say we give some value for it. And we also need to calculate this weight, so we need a mass for this bar. Let's say 100 kilos, for example. And we need to set up what is our the value for our gravity. So let's give that in meters per second square. And we also need some value for beta, let's say a smaller angle, something like this. With these values we could go on and calculate this tension. Obviously we know that weight is m times g, and then we multiply that by the cosine of alpha and divide that by the sine of beta. If we run this program, obviously after giving a name for it, we'll see that we'll have a value for t. But we can make this a bit more interesting if we think of this problem as someone trying to hoist this bar by this cable being fixed here. Maybe you're rolling up this cable and this point here and bringing up this bar. Let's say it's a lamppost, and we want to understand what is the tension on this cable as this angle alpha keeps increasing from nearly a horizontal bar to an upright bar. However, that is not that straightforward, because as alpha changes, beta changes as well. So we need to understand geometrically how to first calculate this beta, and from then we can calculate the tension T. So let us define a few more things in this problem so we can work with the geometry. Let's say that, let's name the points here 1, 2, and 3. And let's say that the bar has a length L, and the distance between where we fix the cable here and this hinge is a distance called M. And also let's call the angle that the cable does with the horizontal as angle gamma. And also let's say that this point here too is the origin of a new reference frame which goes along here with the horizontal and the vertical. So let's first write the coordinates of these points 1, 2, and 3 according to this reference frame center here in 2. So let's define this geometry of our problem. Let's say that the point 1 has an x component of minus m. Right, so if we have this reference frame centered here, point 1 has x component minus m, and it has a y component of 0. It's only horizontal. Point 2 will have x component as 0. It is in the origin, and consequently it has y component as 0 as well. And point 3, regarding the origin here, has the horizontal component as the distance L times the cosine of the angle alpha, and the vertical component of this point 3 is the same distance L times the sine of angle alpha. If we do that, we can then define the angle gamma as the arctangent of the distances relative to points 3 and point 1. So this would be the vertical distance, and this would be the horizontal distance between these 2 points. And so we can define the angle gamma by this arctangent. And there's a mismatching parenthesis here. Once we define the angle gamma, we can look at this triangle formed by the cable, the bar, and the horizontal, the triangle formed by the points 1, 2, 3, and see that we have this angle gamma. We know that this internal angle here is pi minus alpha, and then we can find beta by knowing that the internal angles of a triangle is always pi. So we can come here and say that beta is now, we can say that it is alpha minus gamma, because we would say that it is pi minus alpha minus gamma, so pi just vanishes from there. And once we have our angles, we can go on to the actual statics part of our problem, which is finding the tension T with the equation we already have. Now we need to define these two new variables, so let's give a length m, maybe the value of 5 meters, and also we need the length of the bar, which we can say maybe 1 meter. And also now we don't want alpha to be a fixed value, we want an array of values for alpha, so we can see what happens to the tension T as this value changes. And as we mentioned, let's say alpha starts in a very small value and go from small increments all the way to a vertical bar. So nearly horizontal and vertical. And as alpha is now an array of values, we need to be a bit more careful how we set up the coordinates of our points, because now x3 and y3 will be also an array of values as alpha changes. So instead of using x3 and actually all the components or the coordinates as an array, let's just use scalar values for all these variables, like so. So we don't run into any problems with the sizes of these arrays. Again, because alpha is a value, is an array of values, giving y3 and x3 also an array of values, we need to be careful that here we're going to use the scalar operator, and now we changed the names of all these variables as well. So it's just a bit cleaning up our code. Gamma, as a consequence, will also be an array of values, and beta, as a consequence as well, will be an array of values, and also the tension T, as alpha changes, beta changes, and T will have as many values as the array alpha. So again, here we need the scalar operator to do this division. So let's see how that turns out. We see now that alpha is an array of 50 values, and consequently beta, gamma, and T are also arrays of 50 values. Once we have all these calculations, we can go on and see these results in a figure. So let's plot, for example, what happens when alpha changes, what happens to the tension T. Remember always to put your labels in the figures. So we can say that this is alpha, simply like so, and this is T. And once we run this and generate our figure, we'll see that our tension is largest when our bar is almost horizontal, or when alpha is very small. And as alpha keeps increasing, or as our bar goes into an upright position, our tension starts decreasing fast, and then it decreases more steadily all the way to 0 when our bar is vertical. And an interesting question you might want to think is, how can you decrease the tension on the cable overall? Maybe you can think of changing this point here 1. Would you make it closer to the bar, or to move it away from the bar? Well, to check that, you can simply run all the calculations again for a different value of the distance m, and see what you think, if m decreases or increases for you to diminish the tension in the bar, in the cable.